Hi, welcome back. So in this video, we are going to start by defining the inverse trigonometric functions. So we've gone through the regular trig functions. We have sine, cosine, and tangent, and then we have the three that go with those. So we have cosecant, secant, and cotangent. So in this video, we're going to find the inverses to these functions, specifically for the first three, for sine, cosine, and tangent. So our motivation here is that we want a function to tell us what angle a sine, cosine, or tangent value comes from. So suppose you know the value, you know that the output of one of these functions is something, but you want to know which angle gave us it. And so our inverse functions are going to allow us to do this. So you can imagine we have sine of some angle theta, and it gives us a value a. So the theta is the input, the angle is the input, and the output is some value. The inverse of this is going to look like sine inverse. We use this -1 sometimes to mean inverse. And then this is a function of a, and it equals theta. So here we swap the input and the output. So the new input is that value, and the output is the angle. So rather than input an angle and output a value, we do it the opposite. So we input a value, and it tells us the angle. So the questions that we're going to work with when we're talking about inverses look something like this. So it might be like sine inverse of 1/2 equals what? And this mathematical statement asks the question, what angle gives us a sine value of 1/2? We're going to learn how to do this using the unit circle or reference triangles in another video, but I'm just sort of prefacing the type of question we're going to see. Similarly, we could do cosine inverse of 0 equals what? And so this would be what angle gives us a cosine value of 0? Or we could do tangent inverse of -1, and this would ask what angle gives us a tangent value of -1? So these are the types of questions we're going to be asking with sine, cosine, and tangent inverses. And when I write these statements, I could also think of switching the input and the output and writing them just as the regular trig function. So I could say that sine of something is equal to 1/2, cosine of something is equal to 0, or tangent of something is equal to -1. So anytime we have something written in this inverse function way, we can write it the opposite using the regular function if we want, or vice versa. So it's nice to know that we can go between these two forms of the functions. So before we can do this formally and really define what these inverses look like, I need to make a note. So if you've taken pre-calculus or a college algebra class recently, you might remember that a function must be 1-to-1 in order for it to have a well-defined inverse. So it must be 1-to-1 in that every input has only one output, and every output has only one input. So a function needs to have this property in order to have the inverse. We could make an inverse, but it wouldn't work properly, it wouldn't be well-defined if it didn't have this ability. So for our sine, cosine, and tangent functions, they are functions, so every input does have only one output, but we don't yet have this second quality. So we need to fix the second part that says every output has only one input, and we're going to do something called restricting the domain in order to make this happen. So let's look at our functions here. I'll start with sine and cosine. So here we're checking to see, is it a function? Does it pass the vertical line test? And is it 1-to-1? Does it pass the horizontal line test as well? Okay, so I'm going to look at the graphs in order to do this, and let's start with the graph of sine. So as I do the vertical line test on sine, I see that it is in fact a function. All of the inputs have only one output that goes with them. But as soon as we do the horizontal line test, we can see that there are many outputs that have multiple inputs. So if I said sine of theta equals 1, there would be an infinite number of inputs that give you this output. So pi over 2 gives you this output, -3 pi over 2 gives you this output, etc. And so this isn't working for that yet. We don't have this 1-to-1 quality happening. So what we're going to do is just look at this small portion of the sine graph. We're going to look at it from -pi over 2 to pi over 2. And now if we just focus on this little portion, we can see that it does pass the horizontal line test. We're basically accounting for all of the outputs from -1-to-1 only one time. So we're not including those other parts of the graph where those would show up again. And so by doing this, we are restricting the domain of the sine function. The domain is the inputs, or our theta values, and we're only looking at the part from -pi over 2 to pi over 2. In doing so, we're only looking at quadrant 4 and quadrant 1 if you think about the unit circle. And we're seeing here that the range is -1 to 1. I'm mentioning the domain and range because when we do the inverse, these are going to switch. The inverse switches the domain and the range. We're going to do something similar for cosine. We're going to look at the part from 0 to pi. By doing so, this now passes the horizontal line test, so we're including all of those outputs only once. You might notice here that we could choose lots of different parts of the graph, like why are we choosing the 0 to pi part? This is just the convention that we normally take, and so when you type things with these inverse functions in a calculator, for example, it's going to do this. I'm all for challenging the way things have always been, but I do also want to teach you that this is the way that we normally see these things. So for cosine, we are restricting the domain to 0 to pi, and this would be quadrants 1 and 2 on the unit circle. Then our range is the same, it's from -1 to 1, and I'm mentioning this because we're going to swap the domain and the range for the inverse function. Let's repeat this for tangent. So for tangent, in order to get all of the outputs only once, we're just going to choose this center portion. So we're going to restrict the domain from -pi/2 to pi/2, and similar to sine, this is quadrants 1 and quadrants 4. You'll notice here that we're using the soft parentheses for those endpoints because there are actually asymptotes there, vertical asymptotes, and so tangent isn't defined at those points, and so we don't want to include them. Then our range is from -infinity to infinity since our function approaches those vertical asymptotes and goes on and on forever. So now that we've restricted the domains, we can start to formally define these inverse functions. As we get into this, you're going to see two different notations. These notations represent the same thing, they're just different ways of writing it. So we could have sine inverse of A or arcsine of A. These both represent the inverse sine function. Then we can have a cosine inverse of A or arccosine of A. And we can have tangent inverse of A or arctangent of A. Then, because we are swapping the domain and the range, for our inverse sine function, our domain is from -1 to 1. This is our inputs, so this is our A values. We have to input something between -1 and 1. Our range is from -pi/2 to pi/2. These are our outputs for our angle theta, and so the inverse sine function is going to give us an angle in this range. Then for the inverse cosine, our domain is also -1 to 1, and here our range is from 0 to pi. So this means the function will give us an angle that's in that range. Then tangent has a domain of -infinity to infinity, and the range is from -pi/2 to pi/2, not including those endpoints. I think that having this all written out can kind of be a lot to have in your brain at once, so I like to think about it on the unit circle. So normally our sine function is defined for any angle, but the inverse sine is only going to be from -pi/2 to pi/2. So quadrants 4 and 1. Then our inverse tangent function is the same, so we still are looking at the angles from -pi/2 to pi/2. The inverse cosine is the different one, it's from 0 to pi, and so it is in quadrants 1 and 2. And there you go. Those are our inverse trig functions, and this is sort of the formal defining of them to make everything work out mathematically. So these domain and ranges will become more important as we start to do examples, and we will be doing that in the next video. Thanks so much for watching, and I will talk to you in the next one.